time to continue with our workshop, and we also continue with the series of seminars by Emilie and Johannes and about Monte Carlo and quantum Monte Carlo. And today she's going to talk about the Wick's theorem, the sign problem, and the projective algorithm. Emilie, it's yours. Thank you.
Sure. Thanks, Jefferson. Yes, so I'm going to continue on talking about the Fermion quantum Monte Carlo. Again, the references are the same as before. Check out the ALF documentation as well as the textbook portion if you want to get more details on these things. And then also the last 15 minutes, Fakir is going to introduce some project proposals for the workshop. So that should be exciting too. Okay, so I'm going to pick up where we left off. So I'm going to go ahead and review where we were at the end of yesterday. And so as a reminder, this is the Fermionic Hamiltonian that we're working with, and it consists of the T term, which is the bilinear, and then the V term, which is the specific square form. And you can write it as a sum of these squares. And so anything that's a sum of these squares is going to be applicable. And what we did was we looked at writing out the partition function, and we found a way through introducing the auxiliary fields to write this in an explicit mathematical form using these B matrices that are attached to different time slices that we introduced. And the sum is over these L fields where the L's each take on the values ±1 or ±2. And this is our configuration space, and updates are for these Ising spin degrees of freedom. So again, and Johannes showed how you do updates, you go sequentially in time, and in each time slice, you then update all the spins according to our Markov chain rules. Okay, and then once we have equilibrated configurations by going through the Markov chain, we are ready to take measurements, and that's ultimately what this is about. And if we look at the observable, we can write it in the exact way using the trace with the observable operator in there, divided by the partition function. And then we do this trick where we multiply by a special form of 1. The numerator and the denominator are both the weight of a particular configuration. And then that allows us to then combine this thing into an observable operator for a particular configuration. And so again, we select them according to the probability we want, and then we can compute our observable using these L star equilibrated configurations. So the main point then is we need to be able to compute this observable for a particular configuration. And so that's where Wick's theorem is going to come in. And you've kind of seen some peaks of it even from Francesco's talk earlier, talking about the observables there. But we'll go over more generally what's involved with Wick's theorem. So some assumptions, the operator form that we're using here is going to involve these C dagger C's, n of them in pairs. And then they each have a particular time coordinate, and they each have a particular space coordinate. And then what we're going to do is we're going to relate it to a Grassmann integral. And so to make that work, we introduce a time ordering definition operator, where basically what we want to do is put them in order from the smallest times over here to the largest times over there. And then when they're equal, we actually put the C daggers always to the right of the C's. And then there's also a sign that gets introduced related to the Fermion anti-commutation there with this operator definition. And as a note, this really is an operator that does something. These operators, the fermionic ones, don't easily just anti-commute past each other in reality, because we have the definition when it has a time dependence. There's actually this U operator here, which evolves it in time. And so the definition of there is given. Okay, so this is our observable form. We have the C dagger C's in space and time. And then one can do basically what I did yesterday, the game of the path integral, introducing the Grassmann degrees of freedom and integrating. And what you will get then is the integral here, where see each of these C daggers corresponds to a psi bar, and then each of the C's corresponds to a psi. And so we have the space-time coordinates listed. And so what we want to be able to do now is go ahead and see how this gets computed. So to do that, I'm going to switch to my notes. Okay, so we want to be able to do this integral. And as mentioned before, the two main things to remember with Grassmann integrals is that when you integrate with one variable, psi d psi, you get 1. But then if you have a d psi by itself, you're going to get 0. And so we're going to look at first just computing this simple piece with a C dagger C at different space and time coordinates. And from the slide, and like I said, if you actually did the path integral, introduced your coherent states, and computed the matrix elements, etc., what you would get is this expression right here. So we have the psi dagger corresponding to the psi bar, and then the C corresponding to the psi. Okay, so first, just a note on the denominator. This is actually an integral we saw before yesterday, and it's just equal to the determinant of m. So I'm not going to say much more there. You can prove that this in a similar way to what I'll be showing for the other things. Now the numerator, we have this matrix psi bar m psi, and a way to actually make it easier to compute is to go ahead and rewrite this matrix. And to rewrite the matrix, assuming that it's Hermitian here, you can rewrite it as U D U dagger. Now, in general, you can actually use SVDs instead. In fact, you'll see SVDs tomorrow with Johannes. And so this proof will actually carry on for a general matrix, but I'm just going to stick with the UD U dagger. And so then what I can do then is be able to write this in terms of a diagonal matrix. And so what I'm going to do then is introduce a new set of Grassmann variables, psi bar and psi, where psi bar and psi are related to psi bar and psi in this following way, which will allow me to then get something diagonal. Okay, so let's go ahead and do that. I've gone ahead and I've written those relations up here to keep in mind. And so first of all, we've got the d psi bar d psi. We can, because it's a unitary thing, the Jacobian is just going to be 1, so I can just write this the same as before, but with our psi bar and psi in there. And then this part now is going to be diagonal. So we just get, in fact, I'll write the D matrix first. Psi bar alpha, psi alpha. And then this last part, I need to go ahead and write it as a multiplication. So I'm going to have a sum over gamma, psi bar gamma, and then this should be the U dagger one. That's one coordinate. The other coordinate is our I prime, tau prime. So that's the first one. And then the second one should go the other way. This little delta, and then psi delta. So now I need to think about what happens with this. And so here's where it's important to think about this, how with every d psi, you actually need a psi variable. And so basically for an integral to be non-zero, well, that's what I said, but I'm saying what d psi bar, every d psi bar alpha needs exactly one psi bar alpha in the integrand. And then the important thing here is that now that this is diagonal, the psi bar size always come in pairs with the exact same alpha. So that means that these are all paired up with the same alpha. And so they'll each correspond to something over here. And that means that what remains, even though gamma and delta could be different, whenever they're different, the integral would actually give us 0 for that term. So the gamma and delta they're forced to be the same, basically, thanks to this term. So that's why making it diagonal makes it easier. And so what I'm going to have then is we have these gamma and deltas, and for every term there would be at most one of them if we looked at the sum out here. And so they would take away basically one of the d factors, because we would integrate over this part instead of over that part in this case. So then I would get a product in our sum. I'm going to just sum over gammas only because gamma must equal delta. And then I'm going to do a product over all the alphas that are not equal to that particular gamma, because the gamma is going to correspond to this piece of d alpha. So this is the portion that comes from the exponent. And then let's think about sign for a moment. Thanks to the negative sign here, all of these will just give a positive contribution. You can think about having to anti-commute this past and how the integration works. But these are missing a negative sign, so that we get one additional negative sign when we're thinking about the integration. And then at the end, we've integrated over these variables. So all we have left are the two u's. So we're going to get u gamma, dagger, I prime. Let me write that better. I prime, tau prime, and then u, I tau, gamma, not delta, because everything's gamma now. And then one more note before we go to the next page. We have a product over all the d alphas, except for one of them. And so what we can do is we can actually write that as the determinant of m, because remember, these are just the product of all the eigenvalues, but then we divide by the one that isn't included. So that's d gamma. Okay, so now we've done the integration at this point, and I'm going to put it at the top of the next page. Okay, so like I said, we had that negative sign from before. We have the determinant of m. We have that 1 over d. And I went ahead and moved the sum over here with the two u's. And if you see, what we have at this point is indeed a matrix multiplication, basically. And so what we have is the determinant of m again. And then here, we're going to have u, and then this is 1 over the diagonals. So we can actually just write this as the inverse of the D matrix, u dagger, and then we have our I prime, tau prime, I tau element. And then let's think about basically what this piece is. So we originally said that u dagger mu is equal to d. If I take the inverse of both sides, I get U dagger M inverse U is equal to D inverse. And then I could multiply both sides by the U's. And what I am going to get at the end is just M inverse is U times D inverse U dagger. And so that's precisely what we have here. So when we do the integral at the end, we get minus determinant of M times M inverse I prime tau I tau. And so we have this determinant factor here, but at the beginning, we weren't actually only calculating this integral. We were also dividing by the integral that just had the exponent in it, and that was the determinant. So this determinant will drop out, and what we end up with is this relationship where this piece, this time displaced function will give us the inverse of the large space-time by space-time matrix M, and then that's going to be equal to the Green's function. Okay, so that's the piece where we just had one term. I am going to go ahead and suggest that about what happens when we have many terms. And so I'm not going to write it out in a full way, but remember, the trick had to do with diagonalizing the matrix effectively and being able to write it in this diagonal form. So I'm going to go ahead and write out, or help us think about what happens if we had a C bar C, C bar C, rather than only just one of them. And so if I do that, what's important again is thinking about when the integral is going to be non-zero. And so again, since I have a diagonal term, these pieces must be the same. And so match up pairs of the same things. And so that is going to force over here one of two things. It's going to force either K and L to be equal and M and N to be equal, or it'll force K and N to be equal and L and M to be equal. And so then we can just think through the combinations. And so there's going to be one case where it's non-zero, where K and L are equal and M and N are equal. And then we're going to get a product again over all of the A's, just when they're not equal to K or M, because that's when the integration will occur over here instead of over there. And so then it's a product of AI. And in that case, we have two pairs of these things. So the sign ends up being a positive sign, because we could imagine a negative sign being in front of each one of them. And then that squares to positive. The other case, however, where we're going to match up these two with each other and these two with each other will differ by a sign from our first case because of the anti-commutation. So for the second case, we have the case where K is equal to N, and then M is equal to L. And then we have a product again over I, but not equal to K or M of AI. And so again, we can do something like before, where we could pull out an entire product over all the I's. And so you can envision this in the future, basically being a determinant. And then what we get is delta KL over AK, delta MN over AM, minus delta KN over AK, and then delta ML over AM. And so notice this is actually a 2x2 determinant of things. And you can show by induction, you can basically get when you have So when you have 3 pairs, then you'll get a 3x3 determinant. When you have 4 pairs, you'll get a 4x4 determinant, and so on. And so this is really Wick's theorem to be able to compute these things. Also, I want to note that on the other page, I computed this expression, and it was in terms of the inverse of the big matrix, the space-time by space-time matrix. We can instead write this in terms of the inverse of a smaller matrix, similarly to with the determinants from before where we wrap them up into a smaller matrix. And in fact, you've already seen this expression yesterday in Johannes's talk. So you can also say that this then is equal to this 1 plus the product of the B matrices, where the B matrices are wrapped around such that the tau is exposed. This is the equal time case in particular. And there are a couple of ways you can show that. It's easier in the operator language, I think. And one way you can do it is to use this relation where if you have the C dagger and an operator, you can commute it past in this way, and you'll end up with this summation. And so you can use that property along with anti-commutation to take this C dagger J, move it all the way around back to the starting point, and you'll be able to derive this expression. Another way is to use more of the Feynman style trick of differentiation under the integral. So you can use that as well to get these Wick's theorem relations. So where you introduce, these source terms, and then you take partial derivatives with respect to them and get rid of these etas, which end up being extraneous, but were important in order to get your operators where you want them. Okay, so I'm going to go ahead and stop sharing here for now. And I will go back to the slides. Okay, so here's where we were with the path integral. And then here I give the general expression. So I showed the one case where we just had the inverse of the big matrix, and then I suggested how we would get the determinant. And so it turns out in general, you can write this thing with its n pairs as this n by n determinant of the inverse elements. And like I said, we have m inverse equal to this quantity, this portion from before. And we call this the Green's function. And then this is the form that I discussed in the notes. And this is specifically the equal time form. No, so this is explicitly the equal time form. And so we define it using this notation that you saw yesterday for the Green's function with its dependence on the auxiliary fields. And as Johannes mentioned in his talk, the equal time Green's function really is the central quantity of the algorithm. So as a review from yesterday, the slide, he showed that really these updates, the formula for making updates in a fast way or in a stable way involves this equal time Green's function. So not only is it useful for computing the observables, because it really is the base of these equal time correlation functions, but it's also the base of making updates throughout the algorithm. Okay, so that's Wick's theorem. And now I'm going to move on to the sign problem. So we've hinted at the sign problem a few times in the past already, but let's get specific about what's going on with it and why it's an issue. So this is just sort of a schematic about a lot of the numerical methods out there for studying quantum systems numerically. And each one of them has its own issues. That's why they're all useful for different things. And so the main point I wanted to bring up from this slide is up here we have exact diagonalization sort of methods. And if we're thinking in terms of quantum spins, we have on the order of 20 to 30 spins in typical regimes. On the other hand, we have methods like DMRG, tensor networks, quantum Monte Carlo, and Lefschetz thimble, these other sorts of methods that people are developing. And they're instead applied to the order of thousands of spins. We're talking about quantum spins, often, even tens of thousands of spins. And the difference really is up here, it's the computational power you need or time you need scales exponentially with the system size, whereas down here, you can get away with it scaling polynomially with the system size. And so the big hindrance that stops us from scaling polynomially with quantum Monte Carlo is the sign problem. So what's going on there? Throughout the talk so far, I've been talking about these quantum weights and implicitly assuming that they're all positive because I'm relating them directly to probabilities with the probability distribution. But as we know, with quantum mechanics, we have complex variables. And so when we write down this trace to the e to the minus beta h in general and write it just as a sum of omegas dependent on c's, oftentimes the weights will not all be positive numbers. In fact, since quantum mechanics involves complex numbers, in general, they'll be complex. And in particular for fermions, thanks to the anti-commutation coming from the Pauli exclusion principle, we get negative signs. So there's kind of a specific negative sign problem for fermions in particular. And then I think this is actually a review from what Francesco mentioned earlier today. But you might say, okay, well, yes, these weights are not all positive, but there's a very simple way that you can write them still in terms of positive weights, even if you've identified a particular set of omegas. And that's through reweighting. And so ALF will do this in general. We'll always do this, basically. We'll take the quantum problem and rewrite it in terms of positive weights. Now, how does that happen? Well, we have our observable times our weight divided by the partition function. And so one of the first things that's done is, assuming this omega is complex, you can first do the trick of introducing an identity where you do the real part in the numerator, the real part in the denominator, so nothing's changed. So now you've introduced at least a real weight. The denominator, it actually just replaces it by the real part only, because you know that the sum of the partition function must be a real number at the end anyway. And then the second step involves separating out, doing basically a second multiplication of the absolute value of the real part divided by the absolute value of the real part again. And then the absolute value, the real part divided by the absolute value of the real part gives you the sign of the real part of the piece. And then there's an additional division of the numerator denominator by this absolute value summation. And basically what we've done then is if you look at the purple piece, that's the probability distribution that's sampled and that I'm calling P bar here. And so you can write this observable then in this way using weights that are indeed all positive. So all of this makes mathematical sense. And so ALF will sample then using this P bar and it will return two observables. This observable, which ends up reducing, you can think through if all the weights are positive, but ends up reducing to the exact observable that you'd like if there's no sign problem. But then this observable as well, that gives the average sign. And the thing with that is when the average sign is not actually 1, the calculation time will scale exponentially with system size. And I'm going to go ahead and switch to my notes again to show briefly how that's involved. Okay, so thinking about that here, we have the observable times the configurations divided by the sum of the configurations. And what I'm going...
We don't see your notes.
Oh, whoops. Yeah, I see what you're saying. Forgot to broadcast it.
Good.
Here we go. Okay, so then the numerator and the denominator are the same as before, this general expression. I am going to assume for this demonstration that omega is real. So instead of a phase problem, we're looking at a sign problem in particular. And so what I can do then is I can take this omega piece, this omega weight, and I can go ahead and rewrite it as its absolute value times its sign. So I haven't changed anything yet. And I went ahead and did the same thing in the denominator too. And then I'm going to go ahead and do what was shown on the slide with the reweighting, and go ahead and divide both the numerator and the denominator by this sum of these absolute values of the configuration weights. So then our new probability distribution then is going to be this one. So we can just write the above as the average of the observable times this sign of the configuration. And I'm going to use I'm going to use prime to refer to this new probability distribution. And then I'm going to divide it by the denominator, which was just the average sign. Yeah, and I guess I don't need the C's there anymore because these are just the operators. So this is OS for the prime divided by S. Okay, and so what's going on here? Well, I can write S prime if I think about it. S prime, remember, is equal to this. But that actually ends up being the same as the partition function of our original thing, because this part is just equal to omega of C. So it's the sum over the omega of C's divided by the partition function of the new distribution, the bosonic distribution. Sometimes you can think of this as the fermionic and this is the bosonic distribution. And so then when I think about this ratio, what I have is basically something that's going to be like in the low temperature, e to the minus beta times n, where n is the number of sites, the volume of the system, divided by e to the minus beta n. This energy, some kind of intensive, this energy density basically for the sites. And so this is like the ground state energy. And so this is e to the minus beta n e naught minus e prime naught. And so that's fine. The sign, then what we're seeing is that the sign is getting exponentially small as we ramp up the system size, the system volume. However, we run into a problem when we actually look at the relative error of the sign, because what we want to do is we want to, with this quantity, divide by this number. And so this number, this average sign, is an important thing in order to get the observable. And so when we do that, we can think about the relative error. And like I mentioned at the beginning of Monday, the variance of S prime goes as 1 over the square root of the number of measurements. And then this second piece, 1 over the S prime average, is e to the minus beta and E naught minus E naught prime. But then that's equal to E to the beta n times this quantity divided by the square root of n. And so then that's really a problem, because in order to get a low relative error, we've got to basically keep up with this number of measurements, keep up with an exponentially growing quantity here. And so this really shows that when there's a sign problem, we get exponential scaling with the volume in terms of the number of measurements that we need. And so that's what I've added here. So when sign is equal to 1, we get the first observable is the same as O. These were the two observables that ALF returns for us. And so when you get a 1 for that sign, you really can say, okay, this is the measurement that I need. But when sign is less than 1, the calculation time scales exponentially with the system size. And so then we're kind of back in that more problematic regime where, just like exact diagonalization, where things scale exponentially with the system size. And so this is really what the sign problem is. Okay, so now what about how do we know when there isn't a sign problem? So I think there were even some questions related to that yesterday. So there are some nice results, specifically geared at auxiliary field quantum Monte Carlo. And one of them being if you can have an anti-unitary operator, if you can identify one, and find that when you transform your Hamiltonian using it, it's a symmetry of the Hamiltonian. And then you have these properties. Basically, you can prove that the determinant is always either positive or 0. And so you can look at this reference for more details on that. And one such operator that has these properties is time reversal. And so if you find that when you do this transformation with the fermions, where you have a spin up going to spin down with the minus sign for one layer, and then spin down, spin up with the other layer, and this is a symmetry of the Hamiltonian, you have a sign problems free simulation. So that's one example. And then there's been some progress on basically finding other cases where models are sign problem free. And one thing that's been useful has been introducing a Majorana basis, where you can write these Majorana operators in terms of the fermionic operators. And the cool thing about that is basically from one flavor of complex fermions, you end up with 2 flavors of Majorana fermions. So it sort of gives an extra layer of fermions. And so just like we had the spin up and spin down to help us out here, we now have an extra layer of fermions to play with. And so then some additional class or a class expansion of fermionic models with that are sign problem free has been found. So these are some references related to that progress. There's also a review article that sort of summarizes things. There have been kind of 2 classes that have been developed along these lines, and they overlap quite a bit, but there seems to be at least a slight divergence between the 2 of them. It's kind of described here. And then I also wanted to note there are also world line ways of thinking about things, and it might be more cooked up. I'm not sure. But there are some models that one can identify with interacting fermions and quantum spins, where the spins can actually help the fermions avoid sign problems. So there's some additional ways of getting around them, but they're more of a case-by-case basis. Okay, so one more thing to discuss before I turn it over to Fokker, and that's the projective quantum Monte Carlo. And so, and I think this was discussed a bit or referenced by Jonas yesterday when discussing some of the ALF information in the info file. But basically the projective formalism is another way to get the zero temperature physics. So before we were looking at the trace of e to the minus beta h. And so we could look at, since beta was inverse temperature, we could look at finite temperature physics, for for any given beta. If we instead simply want to get the zero temperature physics, we can introduce a trial wave function, psi zero. And the important thing about this, so this basically is equal to, if psi zero is the ground state wave function, we can write the observable at zero temperature in this way. And so then to do quantum Monte Carlo, what we want to do is, for the projective version, introduce a trial wave function that we know should have a non-zero overlap with the actual ground state. So that's important. And as long as it has a non-zero overlap with the actual ground state, then we can introduce this theta parameter. And as theta gets large, this quantity will go to exactly what we have here, the ground state average. And then we also have introduced a beta parameter to do time displaced correlation functions. And so then the trial wave functions in particular, they have to be Slater determinants. And so they also have to correspond to a unique ground state of a non-interacting problem. So that was another thing about the info file, making sure that there wasn't a degeneracy in the ground state. If there is, then there can be a sign problem there. So this is just an example from the textbook that Fakir wrote, and it just it compares the correlation function and the energies for the finite temperature version and the projective version. And so you can see as a function of theta or beta, depending, the white triangles show the finite temperature version, whereas the black circles show the projective. And so you just see that you can reach the lowest energy faster with the projective because we're getting rid of some of the excited states. And so it's nice if you want to get the zero temperature calculation. And then some things that might be important for tomorrow and for when you're developing your own code, the trial wave function, like I mentioned, it's a Slater determinant, and it has to do with the ground state for a non-interacting Hamiltonian. So if I take a T operator and then I look at the U's that actually diagonalize that T operator, since it is a Hermitian operator, I can do that. Then the U ends up being this important quantity in order to actually get the Slater determinant. Because you can then take this transformed C that would diagonalize the Hamiltonian. You can do a product of n particles. So if the ground state's at half filling, say half of the total number of particles possible. And then you can write it, basically the ground state involving this U matrix that is not a square matrix because it's actually one dimension is the number of sites or degrees of freedom, whereas the other dimension is the number of particles. And then we call this matrix P later on. And so then there's a formula for the Green's function that I'm going to use the same notation as before, because the nice thing is whether we're doing finite temperature or zero temperature, we actually use the Green's function in the exact same way in all of the formulas. It's just the expression for the Green's function ends up being different. And so for a particular tau, you see these products of the B matrices go up to tau here, and then they go up to the rest of LT there. You have the projector matrices, and then in here as well. And so this is how you compute the Green's function for the projector method. There's another advantage where stabilization, which Johannes will discuss tomorrow, is actually much simpler. This is a stable quantity in comparison to the finite temperature one. And then there's also a nice property for the projector one in particular, where if you square the Green's function, you get it back. Okay, so that's what I have to say related to Green's functions, sign problems, and Wick's theorem. And I think, yeah, either if we want to do questions or turn it over to Fokker now, I guess I'll let Jefferson decide that.
I think we have time for questions. If someone has a question, that's a good time to ask them.
I'm just waiting for students. Well, the question, but if nobody wants, maybe Emilie. So, want to ask one question about sign problem, because I still didn't understand. I don't know the answer, so any answer will be good for me. So you said we all know that lattice Monte Carlo is heard from sign problem. But there is another group of Monte Carlo people, which called the diagrammatic Monte Carlo. Maybe you know this Nikolai Prokofiev, who is
the sign blessing
prophet. Exactly, sign blessing. Can you comment on the sign blessing?
Yeah, I mean, it's kind of a nice. It's nice to be positive about it, I suppose. But I think the difficulty there is really. I mean, I don't want to be too negative, but actually being able to do the calculation with it, because I don't know, we've been able to do quantum Monte Carlo with all of these models in a straightforward way. And it seems like, I mean, maybe it's the formalism is developed enough, and I don't understand enough of the details to comment in depth on, but it seems like it hasn't been applied to the actual problems so much.
Okay, thank you. Sign blessing is good.
All right, there's no problem in asking questions about Emilie's talk also later on. But I think now, Faka, if you want to talk about the projects, you could start.
Oh, I think Sandeep had a question. So even if the determinant is positive, but the determinant is non-local quantity, that would affect the fast update. And yeah, I think your point is when we split things up in the interactions for the squared terms, if those are local terms, then when we do our fast update, it really is fast. We take advantage of the locality. But it could be that the squared terms in the potential energy actually are contain all the coordinates and are global. And so in that case, that would affect the fast update, and that would add another volume in there. So yeah, we could have something with not a sign problem, but then the polynomial scaling could be worse.
Okay, thank you, Sandeep. So Faka, I think the podium is yours.
Now, can you hear me?
Yes.
Now you can hear. So this is a set of projects, right? Which are just suggestions, and you can find your own project. So I have 10 projects all in all, including also the project of Jelozinski-Moria interactions, which actually is possible to formulate with the ALF, which was a question yesterday. So here's my first suggestion, and this is a very old article. Well, actually not so old if from my reference point of view, it's not so old. From yours, I guess it's very, very old. So this is a very nice article by Elvio D'Agato and Morris Rice on surprises from 1 to 2D. And what they noticed is that if you take a single chain, a Hubbard chain, which is written down here, and if you measure, this is at half filling, so it's an insulating state. If you measure the spin-spin correlations, then you get something which falls off like it's oscillating -1 to the I divided by R. There's a logarithmic correction. Now, if you go to 2D, you know, you take a 2D square lattice, then you have long range order. And the question they were asking is, how do you go from 1D to 2D by doing some type of dimensional crossover? And the next lattice you would use is basically a 2-leg lattice, which is something like this. So it has open boundary conditions in the y direction, and here you would have a T-perp. And you will notice that, you know,
We somehow don't see your annotations. I mean, we see your slide, but not the annotations.
Aha, so I got the wrong, I think I got the wrong, this is it. Can you see my iPad? Now, can you see my iPad or not? If I write something here?
Yes, now it works.
Okay, thank you. So, so if you put a T-perp, right? That's what they did. If you put a T-perp and the T-perp is very big, then you will build a singlet here, essentially. And then a spin singlet, and what you will get for a 2-leg ladder is something which a spin-spin correlation which will fall off as e to the minus r divided by chi. And so chi is basically the inverse spin gap. And so, you know, then you can go to 3-leg ladders, you put 3 legs and you will find something again, which is a power law, which should actually have exactly the same 1 over r, etc. And you will have an odd even effect until you go to the 2-dimensional case where you have long range order. And the thing is that essentially this length scale, if you keep being on odd ladders, then this length scale will diverge in the thermodynamics. So it's a very nice way of using the ALF. This is just running the ALF because you can use the n-leg lattice, right? And this can, you know, and you can run the Hubbard model, the n-leg lattice, and all you have to do is to analyze the spin-spin correlations, which are also a default variable in the code. That's one thing, which is related to very nice physics. Now, that's one suggestion. It's actually a hard problem, right? I mean, if you really want to go to large lattices, it's not such an easy thing to do to see this. But for 1 leg and 2 leg, and 3 legs, that should be possible. So then another thing which is very nice is staying in the realm of 1-dimensional Heisenberg models, and you know, or Hubbard model, just the 1-dimensional Hubbard model. Now, the 1-dimensional Hubbard model has actually enhanced symmetry. And the fact is that if you measure the spin-spin correlations, then you will see something which is like -1 to the r divided by r. I said that before. In the ALF, we have also have some predefined observables, as Francesco said this morning, some predefined observables measuring the dimer-dimer correlations. And you will see that for the Hubbard model, if you measure the dimer-dimer correlations, you will get exactly the -1 over r dk as you get for the spin-spin correlations. And so this suggests, if you want, that the 1-dimensional Hubbard model has a higher symmetry than the SO3 symmetry. It has an O4 symmetry. And this is actually the case. This was shown, argued by Affleck and Haldane, etc. And if you calculate this, this is pre-programmed. This is not pre-programmed. So this should have the same decay as the dimer, right? But it's a kinetic energy correlation function. And so if you do that, then you will have somehow learned that the 1-dimensional Hubbard model is actually, you know, the physics is dictated, if you want, by a field theory, which is an O4 nonlinear sigma model in 1 + 1 dimension with a Wess-Sumida-Witten term. So I won't tell you all the things about this here. So this should be actually a 3. It's a you know, I think the most elegant or the deepest way of understanding, I think, the physics of the 1-dimensional Hubbard model. En passant, this model here, this field theory in 1 + 1D, you can generalize it to 2 + 1 dimensions, to an O5 nonlinear sigma model in 2 + 1 dimensions with the Sumida-Witten term. And one of the most advanced, I would say, applications of the ALF was to really provide a numerical simulation of this continuum field theory. So that was pretty amazing that this worked out. And very similar methods have been used by Johannes for twisted bilayer graphene, actually. So if you want to find a solution to this, you can look at this paper and you will get it, right? That would be one possible solution. Okay, so interrupt if I go too fast or if I'm too slow, if you don't think it's interesting. SUN, so we stay on with 1D, right? And now instead of going up in, what we will do is define a higher symmetry, right? So when you normally, this is your Hubbard, your hopping, right? And sum over I, and then sigma goes from 1 to 2. Well, in principle, sigma can go to 1 to n, where if n is even, you will have no sign problem. And then the u term is basically sum over I, and then n of I minus n divided by 2 squared, where n of I is basically equal to sum over all the sigma, c dagger of I sigma, c of I sigma, right? Sigma is equal to 1 to n, right? So this is a Hubbard model with SUN symmetry and not SU2, so it's a generalization of the SU2. What you can do is that as a function of n, right, you will come to a saddle point when n gets very big, and you will have a phase transition as a function of n. The saddle point will give you something which is dimerized. Saddle point means that when n goes to infinity, the saddle point approximation, it's an Affleck-Marson saddle point, it's called, and the saddle point will give you some dimerization. And in fact, so you could ask one question, you know, n equals 2 is not dimerized, n equals infinity is dimerized, so there must be a critical n where the dimerization happens, and it happens to be below n equals 4, because you can take the ALF and do the calculation for this n equals 4 Hubbard model, and you should see that you have dimerization. So this is also, there is no programming to do, because the Hubbard model, module, if you want, is sustains SUN Hubbard models in this way, and so you could in principle just run the one-dimensional Hubbard model at n equals 4, and you will see that instead of having power law spin-spin correlations, you will have some dimerization, have some exponential spin-spin correlations. You can also measure the kinetic energy, or dimer-dimer correlations. This is also pre-programmed for the n equals 4, and you will pick up the dimerization. So here, something which would be a bit more involved is to say, well, any Hubbard model, if you take the strong coupling limit, U over T is very big, you should be able to map it onto a quantum anti-ferromagnet. And for this case here, you can do that, and you will obtain an SUN quantum anti-ferromagnet in a representation where you have exactly 2 electrons per site, if you have n equals 4. And you can look up in the documentation to look at SUN condo lattices. And if you get to understand this SUN condo lattice, then you will understand how to implement an SUN quantum anti-ferromagnet, and then you can start playing with this, quantum anti-ferromagnetic magnet instead of playing with the Hubbard model. But you will get the same answer. You will not learn anything physically, but you may want to play with Heisenberg models as opposed to with Hubbard models. But the physics is the same for Huffman because there's a charge. Okay, so this is project number 3. Project number 4 is, yes. So the ALF has an implementation of maxent. So many people say maxent is bad, and then maxent, you know, ooh, this is don't use maxent. And maybe you're right, but maybe not, right? So you should try it first yourself. And this is what I propose, right? This is what I propose. Take the one-dimensional Hubbard model where you know the answer from Bethe Ansatz. Well, it's not directly from Bethe Ansatz, but Jean-Sébastien Coe had some very nice results for this. You know the answers from experiments, and you know also the answers from DMRG, right, where it works. And so you would have, what I suggest is take the Hubbard model, n equals 1, U over T equals 4, beta 10, and a pretty large lattice, 46. And you calculate the spin-spin correlations dynamically. So look in this is done in principle. If you look at the chapter 10 in the documentation, you will see that. And here you have the dynamical spin-spin correlation. You will see here the 2 spin-on continuum, right here. The 2 spin-on continuum, it comes out actually very nicely. So this is something you should be able to reproduce with the quality of data, which is not too high. Of course, you will not be able to reproduce how this lower edge diverges as a function of omega, etc. But you will have a very good idea of where the overall weight is. Here you will have what happens to a single hole. This is a single particle spectral function. What happens to a single hole when you put it into a quantum anti-ferromagnet in 1D? Well, it will split up into a spin-on, into a hole-on. If you look rather carefully, this would be the hold-on, I think, and this would be the spin-on branch, I think, and this are shadows of the hold-ons, etc., by a pi scattering of the spin-ons, etc. So you will see, first of all, a gap, but you will see very big structures, which are telling you that the single particle Green's function of a one-dimensional insulator does not have poles, but has branch cuts. That would be the key point. Of course, it will be very hard with Maxent to see the difference between a pole and a branch cut, but you can see at least how the weight is distributed. If you take the same Maxent and you put U equals 0, then you will get a delta function. This delta function will come out very nicely. So as a function of interaction, you will see that you get something very different than a quasi-particle. These are the charge-charge correlation functions, dynamical, where the U over T equals 4, the single particle gap is of the order of 0.7. And so this is twice the single particle gap, 1.4, something like that. So this is gap that's a bit more featureless than the single particle and the spin-spin. So I encourage you to do this, right? And then go up and get some papers from DMRG, compare your results with DMRG, and you'll see that at least for this, you don't do so bad. And it will give you also an intuition of how good your data should be to be able to be competitive with DMRG. Well, competitive with DMRG you will not be, to be very honest, but to have at least some good idea of what happens. That's very important, because a lot of the things we do, if you want to compare to experiments, then you need some type of an analytical continuum. How am I doing with time? Should I stop here and continue tomorrow, Jefferson?
I think it's okay if you do the fifth model, and then for tomorrow you have the other 5.
The fifth model are correlation effects in topological insulators, right? Essentially topological insulators. So this is something you have to program. So that's a bit more involved already. We don't have any predefined hopping with for a topological insulator. So this is the model I suggest to program. So we would stay on a square lattice. This is my square lattice point. And what we have is that we have a pi flux model. So what does a pi flux model means? It means that if I go around a plaquette like this, then I will always pick up a minus sign. That means that there is a pi flux, if you want, which goes through each plaquette. How do I do this on the lattice? Well, essentially, all these hoppings which are here, let me give you another color, all these hoppings which are here, right? They will have an opposite signs as the hopping which you see here, right? So if you do this, so this is actually the pi flux in the Landau gauge, actually. And if you do this, then you see that because you have a minus hopping here and a plus hopping here, then the unit cell is a bit bigger. It's a 2-site unit cell. So this pi flux is a lattice discretization with C4 symmetry that's sometimes useful of a Dirac system. So this H Dirac is essentially what I wrote here. Now, what you would like to do is to generate out of this Dirac system a topological insulator, a quantum spinol insulator. And so, so the quantum spinol insulator is a mass term, if you want, in a Dirac in the continuum. And this is a generalization of the, so you maybe know the Kane-Mealy model. The Kane-Mealy model is on the honeycomb lattice. And what is written here is essentially a rewriting of the Kane-Mealy model, but on a square pi flux lattice, right? So this term here, if you put it, that will open up a gap in the Dirac system. It will open up a gap here in the Dirac system. Here is my pointer. It will open up a gap in the Dirac system, and it will be a topological insulator. You will have some edge states. Okay, so you have now a band structure. It's an insulator at half filling. You can dope it, right? You can dope it, and you can ask the question, which I think Johannes asked himself rather recently, is what happens to superconductivity in topological band. So he had topological flat bands. This is not yet a topological flat band, but it's a topological band. So you can do that if you you will have no sign problem if you add an attractive U on the A's and on the B. So U would be negative, and then you can dope with a chemical potential, and you can show that this model, because of what Emilie showed today, once you do the formulation, it has time reversal symmetry, right? That you have no sign problem at any U, right? At any negative U, right? If you have a positive view, then you need to have a chemical potential of 0. So what I suggest for this one is certainly a bit more involved, but it opens a nice set of a rather big playground, I mean, on which we lived for some time, I must admit. And then so you have Dirac systems, you have topology, which comes into here, you have correlation effects in topological insulators, etc. So you can look at helical liquids on the edge, etc. So actually the helical liquid was to look at this for the, I mean, this is 5 and 6 are very similar. So apologies, I'll do the 6 also. The 6 would just be the same as the 5, but instead of doing this with periodic boundary conditions, you would have to take the Leg Lattice class, if you want, and then put this on open boundary conditions. When you have open boundary conditions, you have these edge states, which are characteristic of topological insulators. You can really look at them, and you can look at the physics, if you want, correlation physics on edges of topological insulators. And what you should obtain is basically a realization of a Luttinger helical liquid, a helical Luttinger liquid. Sorry, I got it wrong. So this is a big, you know, these two things are a bit more demanding in the sense that you will have to play around with the band structure, right? You will have to implement your band structure so as to be able to introduce this quantum spin Hall. And if you do it, then we could actually include it in the code. That would be very nice. As Francesco said this morning, you know, everything which you do, in principle, could be included in a new release of the ALF. Okay, I'll stop here. And I have then 4 more subjects for tomorrow after Johannes' talk, and I'm ready to take questions if you have any questions. So no questions. Everything is crystal clear. Sasha has a question.
If you want question.
Yeah, if you want a question, ask Sasha. Right? Yeah, perfect. That's very good. Thank you.
I'm very interested. So about your how to say ladder, yeah.
Yeah.
So 2 years ago, it was a very good science paper we discussed from Tom DeVroe group. What they did, they used DMRG and calculate 4 times 64 ladder, 4 times 64, and it was the first paper from DMRG that they find a long range D-waves correlation. There is also fight between this New York group and Stanford that this 4 is small.
Yes.
But do you try or think to really to simulate this? So you see, it will be very good answer if you can simulate 4 times 64 with your ALF, and then maybe 6 or 8 times something. And
well,
just
that's feasible. Just that they so Tom did that in that was at finite doping, right?
Yes. So Tom did a very good job. Yeah. You need to put T and T prime something, T prime over T minus 2 or minus 3. And Tom put 12% doping.
Right.
Sorry. And Tom put 12% doping, 12.5.
So I don't I believe that I believe that the sign problem could be rather severe there. But you could certainly try it with high temperatures and see what happens as a function of temperature. But it's not so clear. Yeah, Sasha I think is phoning now, so he asked the question phoning. But we could certainly try, Sasha. Okay, other questions? All right, Sasha, another question. I think I can stop also the recording if I find